Okay, things are going on in Germany, things are going on in England, and the status in the US is that Enrico Fermi, the Italian Nobel laureate, and Leo Szilard, the Hungarian Jew, who is now in Colombia, were working on trying to see if they could build a chain reaction to make what would then be called a reactor eventually. And of course, you needed uranium ore, you needed graphite to be the moderator, to slow down the neutrons, to cause a chain reaction. Finally, money was starting to flow. Finally, the US government was realizing this should be a priority, especially after Pearl Harbor. The other thing that was happening is that element 94 was discovered by Seaborg at Berkeley in the past year. Fermi thought he had found that when he did his experiments in Rome, but he misidentified things. So finally, Seaborg discovered plutonium-239, and then they also found that plutonium-239, though it does not exist in nature, if you can make it artificially, it's an even better fission source than uranium-235. And the way you make it, people realize by this time, you make it by capturing a neutron on the abundant isotope of uranium. So if you could build a chain reaction, if you could build a pile of uranium-238 with a moderator in the form of graphite, then you ought to be able to breed and make plutonium-239, which is an even better fission source than uranium-235. So he called it a pile, Fermi did, because it would stack up a pile of uranium interlaced with graphite. And he was assembling his first pile in Columbia University in New York. And his pile was a lot of graphite. He had to find pure graphite. Szilard was the real dealer. Szilard was the guy who could get things done. He went out and found pure graphite. Remember the case in Germany where Walter Botha made a mistake and probably had somewhat contaminated graphite. It's often contaminated with boron. And he measured that graphite would not work as a moderator because it absorbed too many neutrons. Szilard found really pure graphite, which made this experiment possible. Then they had 8 tons of uranium oxide from ore. George Peger was the dean of the College of Science at Columbia. He found a room for Fermi to do this. They needed help in assembling this 38 tons of stuff in a pile. Well, that was hard for these scrawny physicists to do. So they got the football team. This is before the days of free room and board and all that. And so the players on football, they had to earn money. Well, they earned money by lifting these blocks of graphite and uranium oxide to help Fermi assemble the pile of material. So that's what Fermi was trying to do. He was trying to show that you could work toward a chain reaction. You multiply neutrons where one uranium nucleus fissions, giving off a couple neutrons, and then that would make other uranium nuclei fission, and you'd have a progression, more and more neutrons. The way Fermi decided to measure this, he invented a number called K, reproduction factor. And so that's what that number means. That's the number of neutrons you produce per neutron emitted. And so if uranium fissions and gives off, they weren't sure, 1 or 2 or 3 neutrons, then if K is greater than 1, then you are increasing the number of neutrons as you have different generations of fission going on, one event after another. If K is less than 1, then it's not going to be a chain reaction because you're not producing enough neutrons to keep the chain reaction going. And so that's what he was trying to measure. As he assembled this pile, he invented ways to try and measure what the multiplication factor, the reproduction factor would be. And that's important. You know, when you have the first fission event of a uranium-235 nucleus, you get K neutrons. then those each cause another fission, and so you get K squared at the second generation and K cubed. Well, that's a chain reaction, a geometrical progression. If that would work, could then be a bomb or a reactor. And so that's what he was trying to measure. When they first made their pile of uranium plus graphite in Columbia in fall of 41, the K was too small. It was less than 1, it was 0.87. He calculated it in different ways by the measurements, trying to measure the number of neutrons created. Well, he had to improve the pile, and so they made some improvements. They got rid of the iron cans into which the uranium oxide was packed. They were assembling those, stacking those cans. Cans reach about this big to get to 30 tons of uranium oxide in this big pile. Well, they got rid of the iron because that absorbs neutrons a bit. They got even purer graphite. Szilard found that with even less boron. And then they improved the geometry by machining the uranium into spheres. Little spheres of uranium surrounded by graphite. And so he kept trying to increase the efficiency at which neutrons would cause other fission events. At the same time, this uranium committee was getting more recognition, more prominence in the US government. Why is that green box there? That's annoying. Well, that's related to the Zoom business, I guess. Stop share. Okay. I don't understand that. Okay. Well, I have to live with that green box. That shows that it's being shared. And it probably means it's only stuff in that green box that's being shared on the video. So I'm not sure why that is. Nope. Oh well. So by the way, the name of this uranium committee then got changed to the S1 program in this new Office of Scientific Research and Development, reporting to the president. So they met in December. The first meeting of that committee was not long after Pearl Harbor got attacked. That was December 7th, this was the 18th. And of course, secrecy was becoming paramount. And so they invented code names. And so copper was a code name for plutonium and magnesium was a code name for uranium. So that if there were spies around, they would get confused. And Arthur Compton, the Nobel laureate from Washington U, now at the University of Chicago, proposed a timetable now that this is all being taken seriously after years of delay. That the hope was there could be a chain reaction achieved by 42. Production soon thereafter of a reactor, then do a pilot plant to start to make plutonium by October 43. And then you would have usable plutonium fabricated, separated by December of 1944. But the key in this pathway, making a plutonium bomb, was could you make a chain reaction? Could you build a reactor? And that's what Fermi was working on. Initially, they thought that building that chain, making a chain reaction, building a pile, building a reactor should be done in Columbia. That's where Fermi and Szilard were. And but then they realized that the work on the chain reaction, building the pile, and on how to extract plutonium, the chemistry of that should be done at different places, in part for security. Compton was now in Chicago, the University of Chicago, so they decided to locate that there. Of course, there was debate. Fermi wanted all that to be in Columbia. Lawrence wanted all that to be based in Berkeley. So that was the question of where to locate these different parts of the experiments. At the same time, around the time of Pearl Harbor, you know, Hitler tried to take Russia. Napoleon made that mistake, and now Hitler made that mistake. And so on December 6th of 1941, the Soviet forces then did a counterattack on the German troops as they were 30 miles outside of Moscow. Of course, it was cold. The Russian troops from Siberia were used to this, so this was not a problem for them, but the German troops were not. And the Nazi army got beat badly in this counterattack by General Zulauf. And so that was a big loss for Germany, and they got rebuffed by trying to take Moscow. Hitler fired his army commander, and he assumed that responsibility himself. Well, that made a big change in Germany. Resources now got very tight. The war all of a sudden was not going quite as well as before. Their uranium committee got downgraded since resources were tight. It downgraded in priority, and downgraded where it would report. It was now put into the Ministry of Education, of all places, Heisenberg's uranium committee. Heisenberg and his physics colleagues were not happy with this demotion. To counter that, he organized a meeting in February of 1942 to invite some German leaders to hear what his group was working on relative to a possible atomic bomb, as they had been put off into the corner. A lot of the German leaders did not come, but Albert Speer did attend. He was the Minister of Armaments and War Production. He was close to Hitler. And so Speer attended, and Heisenberg then made a presentation about these possibilities. He initially stressed this as a form of electricity production. Primarily, that this idea of using uranium would be a way for Germany to have a uranium motor, a way to make electricity to power tanks or whatever. But he also discussed a bomb. Either possibility, either a bomb built upon uranium fission or on plutonium fission. By this time, both sides understood those two possibilities. That didn't produce a commitment, but then in June, Speer came back, brought with him Porsche, Ferdinand Porsche, you know, the vehicle. This is the industrialist who started the Porsche automobile company. And so Albert Speer brought Porsche with him to learn about the secret weapon. This time Heisenberg went right away to the possibility of a bomb. He had to get the attention of the Third Reich to get back into full support. And Speer said, how long would it take you to do this? Heisenberg hedged his bets a bit, said it would take some years to develop, at least 2 years minimum, and he really was going to be difficult because Germany did not have cyclotrons to do measurements, to do the crucial measurements of how much graphite or other things would absorb neutrons as they tried to build a pile, to build a chain reaction. They asked Heisenberg how much money you need. He said a few hundred thousand marks. And Albert Speer was saying, is that all you need? You should ask for a million or two. But Heisenberg said, they don't need that much. But at least he had the ear of the Third Reich now. Speer went to see Hitler, told him that the physicists weren't really sure they could build this bomb. Speer was skeptical that you could build a bomb in time. And so they decided to give some support, but as a power source. So that's one crucial point where the focus at the highest level in Germany turned away from building a bomb and instead focused on building a power source to make electricity. for the German war effort. Well, we didn't know that, of course. Our assumption was that with Heisenberg in charge, that Germany was trying rapidly to use uranium fission or plutonium fission to build an atomic bomb. But apparently at that point, June of 42, the direction changed. March of 42, Vannevar Bush went back to the president. And Bush had been delaying this focus on uranium fission for a couple of years. But after Pearl Harbor, everyone started taking this more seriously. So by this time, Bush went to see the president and said, you could do this. You could build a bomb with only maybe 5 or 10 pounds of fissionable material. And it would have a blast potential of at least 2,000 tons of TNT, a huge weapon by those standards. You would need to invest, Mr. President, in building a centrifuge plant to separate the uranium, or a gaseous diffusion plant to enrich the uranium in mass-235, or electromagnetic separation facility to enrich uranium in mass-235. So if you did one of those things or all of those things, that you might be able to have a weapon by 1944. And the president told Vannevar Bush to proceed. And so it had changed now all of a sudden. Before that, the US didn't have this physicist in the US did not have the go-ahead or the money, but now money was not the problem after Pearl Harbor. It was full speed ahead, trying all of these scenarios because there was not time to try this separation enrichment strategy. If that didn't work, try this one and so on, because they were convinced the Germans were ahead of the US by a year or two. So then in May, Conant, the president of Harvard, part of this uranium committee now called S1, had a meeting and talked about the 5 ways you can get to an atomic bomb by different strategies for enriching uranium or by different strategies for producing plutonium. The committee shared intelligence on where the Germans stood. The German indeed, by this time, had gotten a ton of heavy water from Norway. Well, they knew what that meant. That meant that they were trying to use it to moderate neutrons and building a reactor in Germany. They knew that the Kaiser Wilhelm Institute was working on their atomic bomb project. They knew that spies were trying to find out the status of the American effort. And the analysis was that probably the Germany was ahead of the US by at least a year. And so time was crucial. And that's why one had to try all of these strategies at the same time instead of doing one after another, because surely the Germans were at least a year ahead of the US in this uranium project. Compton, Arthur Compton, the Nobel laureate from Washington U, had moved to the University of Chicago. The lab he was running there was called the Metallurgical Lab. Once again, they weren't working on metallurgy, but it was like Heisenberg calling his new facility in Berlin the virus lab. Just not really what they're doing, but to deceive people. That's where a lot of this work was going on. Glenn Seaborg arrived from Berkeley, he was 30 years old, to take the lead on figuring out a way to build a plutonium separation lab. He discovered plutonium, element 94. Fermi was trying to figure out how to build a pile, a reactor, and so Seaborg's responsibility was trying to figure out how to separate out minute amounts of plutonium if you could create it in a reactor at a very small concentration, maybe 250 parts per million to do chemistry, and that's what was unheard of at that time. he had to invent a new way of doing chemistry, microchemistry, with a lot of radioactive pieces. And so they had to invent remote control manipulators to do this kind of chemistry. They had a conference of experts, Wigner and Urey, a Nobel laureate in chemistry and so on, to talk about how to do that separation. Mark Miller would know more about this, but they hit upon an oxidation reduction process. Plutonium in different oxidation states, different charge states, has different chemical properties. And to separate out this small needle in a haystack, you had to do some very novel chemistry reactions on very minute amounts of plutonium to separate it from the mass of uranium-238 in which it was encased. And so by changing the charge state of plutonium atoms, you could do that separation in multiple steps. A very heroic development of the chemical process. They had to develop these tools of microchemistry. To work on that, before they had a pile reactor, they took a lot of uranium oxide to Washington University, where there was a cyclotron. And with a cyclotron, you get protons that hit beryllium to make neutrons. And they subjected these 300-pound batch of uranium with neutrons, cooked it, so to speak, bombarded it for weeks or months in order to make material that had plutonium embedded in it, so that Seaborg's team could start to experiment on plutonium chemical separation strategy with that, not that bomb material, but with uranium with small amounts of plutonium in it that was produced by neutrons on uranium. So that was, Seaborg arrived in Chicago to take the lead on the plutonium chemistry lab April 19th of 1942. The same day was the Doolittle raid on Tokyo. Remember, Pearl Harbor was catastrophic for the US Navy. A lot of our battleships were sunk. December 7th, 1941, US struck back at Japan in April. Jimmy Doolittle led an attack. 16 B-25 bombers took off from aircraft carriers that had sailed over near Japan, or over that part of the Pacific, out of Hawaii. They did a surprise run at Tokyo. They attacked Tokyo, these 16 bombers, and Japan did not expect that. The plan was to bomb military targets, but also then to show Japan they could be attacked. These aircraft carriers were not big enough for these heavy bombers to land back on them. And so the plan was they would then attack Japan and land in China. And it was successful. It killed, these bombing raids killed some civilians. I mean, the toll wasn't really high, but the psychological toll on Japan was great. And that was the idea. The idea was to pay the Japanese back from Pearl Harbor somewhat, to spook them that they could be attacked in their homeland, and to boost American morale that had taken a big hit after the Pearl Harbor attack. All 15 of the 16 bombers, B-25s that attacked, dropped bombs on Japan. 15 made their way to China. They all crashed on landing, but most of the airmen, 5 per plane, survived. One landed near Vladivostok in Soviet Union, off track. Soviets captured that crew, and they were held for a while, for more than a year, before they were allowed to kind of escape to Iran. The Japanese were not happy. They then attacked that part of China, killed 250,000 people to try to inflict retribution on China for letting the US bombers land there. So there was hell to pay in China by the Japanese. In Japan, it really raised questions in the minds of the citizens whether the military could protect their homeland from attack. And so it was, and of course, the Japanese employed that for propaganda purposes, that they were under attack from evil Americans. That led in part to Admiral Yamamoto's decision to attack Midway Island. Remember, Yamamoto was the mastermind of Pearl Harbor. And with all this uproar over these 16 bombers dropping bombs on Tokyo, Doolittle raid, he decided that they would attack Midway. And that was the famous Battle of Midway then, thereafter. See, Midway is here. Japan is here. The Japanese were taking things, taking the Philippines and so on. They were wanting to extend their boundary. They wanted to take Hawaii. They had crippled the U.S. naval fleet in Hawaii. The next step was to take Hawaii, to take Fiji, and so on. So Yamamoto wanted to expand out their net. And so he planned an attack on Midway, the next step, after the Doolittle raid on Tokyo. Luckily, American cryptographers broke the code and learned that Japan was going to attack Midway. They learned the date and the time at which Japan would attack Midway. That enabled the US to set a trap for Japan as they came to try to bombard and take Midway. That was a crucial defeat because they broke the code. Crucial defeat for the Japanese. 4 of the aircraft carriers that came toward Pearl Harbor in December of '41 were sunk. In the Battle of Midway, the U.S. lost 1 aircraft carrier and destroyer, but it was a bad defeat for Japan. That and the Guadalcanal campaign were the turning points in the Pacific War. Back in Chicago, the development of this chemistry to separate plutonium was continuing. So after they did this irradiation of 300 pounds of uranium hydroxide, I guess, they then had
uranium nitrate.
Nitrate. Yeah, right. Of course. Right. Nitrogen, hydrogen, uranium nitrate. Nitrate hydride, or?
No, it's uranium nitrate hydrate.
Okay.
So it's got waters of hydration associated.
Okay. Good. It's good to have a token chemist in the room. So they had this uranium material. They had cooked this for a month in the cyclotron at Washington U in St. Louis, brought it by truck. And now Seaborg's team had the material to start developing these tools of hot microchemistry. They had a little room, not very good quarters. 2 young chemists took the lead on developing these techniques. And you could tell, because of radioactivity, they would do the chemical separations, change the oxidation state of plutonium, do a separation from the massive material in which these minute amounts were buried. Know if you succeeded by looking at these activities. Plutonium, the decay of, you had neptunium in there, you have plutonium, you could tell something about their half-lives, whether you had separated out what you needed. And finally, after a couple of months of work, on August 20th, these 2 young chemists, working day and night, succeeded in separating out a microgram of pure plutonium from these irradiated 300 pounds of this uranium compound, chemical compound. So finally this worked. And so now Seaborg knew how the chemical reactions that you would need, how to scale this up. Gregory Bright was another person who was involved in Chicago. He was working with people in Chicago, faculty member of the University of Wisconsin, German. He was also paranoid about security. He did not like Fermi always talking about openness, sharing results, discussing how to do these experiments, these processes better. So Gregory Bright quit. He was in charge of thinking about fast neutron studies and in charge of starting to think about how to design a weapon. When Gregory Bright quit, that's when Arthur Compton brought in Oppenheimer. Crucial step. Oppenheimer then became the most important leader of the project, but this is when he was brought into the project officially. And Oppenheimer then, in the summer of 1942, hosted a summer study group in Berkeley, gathering some of these people, since Compton put him in charge of this effort to think about what a weapon would be like. So this group of people went to Berkeley for the summer of 42 to think these thoughts about how you would design a weapon. Teller, another Hungarian Jew, Van Vleck from Harvard, Hans Bethe, who came from Europe when Hitler turned up the pressure. Serber was a student of Oppenheimer at Berkeley, and a few other young physicists. So they spent the summer working in Berkeley. Edward Teller got obsessed with the idea of a fusion bomb. In other words, a hydrogen bomb. You see, this is a plot of binding energy per nucleon versus number of nucleons in a nucleus. In other words, if you start with uranium and let it split into two, the products, two nuclei about half the mass of uranium, have a higher binding energy per nucleon. In other words, those two fission products are more tightly bound per nucleon than uranium was. Well, E equals mc squared. That means when uranium splits into two, you have to get rid of mass, because these two are more tightly bound. They have less mass than they should. And that's where the energy comes from. That you get energy emitted when uranium fissions. Thus, that's what people were working on from 1939 onward. Also, you see, you get energy, a great deal of energy, when you take hydrogen and fuse it. The binding energy per nucleon goes up dramatically from hydrogen to helium to lithium, so on. Well, that's a fusion reaction. That's how stars burn. The universe is mostly hydrogen. Stars are mostly hydrogen. And the why our sun is hot is because you have hydrogen fusion going on, and because the product of that has more binding per nucleon, then you get rid of a lot of mass, a lot of energy. Well, that was Teller's idea. Maybe you could build a fusion bomb to replicate what goes on in the sun. Well, they studied that summer. That you might have a fission bomb that would give you the temperatures needed to make fusion go on. And fusion would be deuterium plus deuterium. Deuterium is heavy hydrogen, an isotope of hydrogen. That they knew from physics studies that you can make two deuterium nuclei fuse to make helium, give off a neutron, and give it some energy. Or you can fuse to make tritium, and you get some energy. Well, you get less energy, 3 MeV or 4, compared to the 170 MeV you get when uranium fissions. that looks not favorable. On the other hand, the advantage of a fusion bomb, you don't need a critical mass. See, that was a problem, to multiply neutrons, have a chain reaction, have enough mass that you could make a uranium bomb blow up. That's not the case for fusion. And so, you know, if you got that temperature, then the fusion reaction would continue to burn until you ran out of deuterium. Another advantage is you could then separate heavy hydrogen, deuterium, from natural hydrogen far easier technically than you could separate uranium-235 from natural uranium. We knew how to do that at that time. So Teller was obsessed with building a fusion bomb. And if you could make that work, because that slope is so high, a fusion bomb would have a blast potential 500 times greater than a fission bomb. Well, you know, that's what we have now. Our nuclear arsenal in the world are not these little uranium bombs, they're hydrogen bombs, they're fusion bombs. And things dropped on Hiroshima and Nagasaki pale in blast potential compared to the current plethora of hydrogen bombs we have on Earth. Well, that's what Teller was proposing. You might have to have an atomic uranium bomb to detonate, to get enough temperature to detonate a hydrogen bomb. During that summer of study, they realized that the problem is that fission, the fission bomb is too slow, and it might tear apart to get that temperature, the fission bomb might tear apart the deuterium components before it could explode. And so they looked at another fusion reaction, deuterium fusing with tritium, also an isotope of hydrogen. And that we knew about, that gives off energy in a neutron. In fact, you can use that neutron to hit lithium to make more tritium, which is radioactive and does not exist in nature. And that would ignite at a lower temperature. And so it would proceed faster. And so they played with that, of how you would design a hydrogen bomb based upon fusion. Well, that's what our hydrogen bombs on Earth do now. It's deuterium, which you get is stable, you get out of the air, and then you make tritium in a reactor with a 12-year half-life, and that's why we have to make tritium to replenish the hydrogen bombs that the US has, and Russia and China, and I don't know who else, France, and whatever countries have hydrogen bombs. So that's what they talked about that summer. A worry came up then that Teller said that with those temperatures, when you explode a hydrogen bomb in the atmosphere, you might have enough temperature to ignite the atmosphere. You might have enough temperature to ignite the deuterium that's present in the atmosphere. You know, we have water vapor, we have H2O in the atmosphere. Some of that is deuterium. And so if you blew up a hydrogen bomb in the atmosphere, it's possible, he thought, that you might have enough local temperature and energy to ignite the deuterium in the atmosphere. And so you might, he worried, burn up the atmosphere by building and igniting a super bomb, a hydrogen bomb. And his calculations indicate that this might actually work, might actually happen. It'd be a big problem, of course. And I think Compton said it right. If that's the case, it'd be better to live, for mankind to live as a slave of Hitler than to destroy the Earth by igniting the atmosphere with a hydrogen bomb. So this group of physicists spent a lot of time that summer studying this theoretically. And finally, at the end of the summer, they finally decided that it was not a problem. That there was not enough energy, not enough temperature in a fusion bomb exploding the atmosphere to ignite the atmosphere. And so, yeah.
May I insert a
Yes.
story?
Come, Ray.
This particular problem that we're talking about here on the hydrogen bomb was actually the experiment that proved that it would not ignite the nitrogen in the atmosphere or deuterium in the atmosphere. It was done by a man by the name of Alex Zucker. Alex, his first job right out of college, physicists coming to Oak Ridge, was to use the calutrons at Y12 to do this experiment to see if in fact that ignition would take place. And he literally proved that it would not happen, that you couldn't get enough to start that reaction that they were afraid of. Now, 2 parts of his experiment still exist at Y12 and are a part of the Manhattan Project National Historical Artifacts, a part of his power supply, and another piece that he had used to insert into the Calutron still exists there. Alex went on to be the associate director for the Oak Ridge National Laboratory and was an acting director for a few months. And he was also very much into music. He was an active member of the Civic Music Association in Oak Ridge. A good friend of mine in Rotary till he passed away a couple of years ago. So there's a little inserted story for you.
Yeah.
About Alex.
Oh yeah, I knew Alex Will. He was kind of one of my mentors
Yes.
through my career.
Very quiet man. He didn't talk a lot about what he did.
Yeah. And in the summer of 1998, I was head of the physics department, and Alex came to me and said, DOE is going to compete the contract to manage the lab. UT should get involved. I said, oh, Alex, you're crazy. Well, he was right.
Yes, he was.
So by fall of 98, rumors were getting more prevalent, and so we formed a committee here at UT to look at how we would compete for the management of the lab. And Alex was on that committee, and he guided us.
Yeah.
And of course, we then chose Battelle as our partner, and we won the contract. And so Alex was the first to tell me, you better get ready.
That's interesting. Small world.
Small world. Yeah, so Alex came from Yale, as I recall, with his PhD. Came around 1950 maybe to Oak Ridge.
Yes, that's right.
And he tells the story that when the cyclotron was built at Oak Ridge National Lab around 60 or 62, somebody that funded nuclear physics at ORNL called him and said, why don't you send us a 1-page proposal for building a cyclotron? So Alex wrote that up the next day, and 2 weeks after that, they had money to build a cyclotron.
That cyclotron was built in building 9204 dash.
No, this,
9201, in Alpha 2, 9201 dash 2.
no, I think this was Oric,
Or it's a different one.
right, different one. It's a later one.
Yes.
Later
yes,
one. He worked on that one first in the 50s.
Yes, that was there earlier. Is
Right.
it still there today?
And so is the
No.
one at ORNL.
Yeah.
But the point was that in that case, the way to get money to build a cyclotron was very simple compared to now. So anyway, Teller was obsessed with the super bomb. They decided it would not burn up the atmosphere. But Oppenheimer didn't want to be diverted in the Manhattan Project, but Teller was such a strong force of nature that the super bomb was now part of the Manhattan Project, also requiring heavy water if they're going to really work on this. Still, spring of 42, summer of 42, no clear pathway you had Fermi trying to build a pile to make a chain reaction. You have work going on here and there. They were starting to talk about building things. There's still debate about, is everybody going to have to become an Army officer to work in this government project? Things were in disarray. And so Vannevar Bush saw the problem here, that he needed a strong government leader of this project. Probably somebody, not from the private sector, but somebody perhaps from the Army Corps of Engineers. So the US government appointed Leslie Groves to take the lead on this project. Let's see, who's doing Groves? What did we, oh no, she was doing Groves, right? So he was, a distinguished guy, graduated from the University of Washington in the Northwest, was at MIT for 2 years, went to West Point, graduated number 4 in his class in 1918. He took the lead in building the Pentagon. So he was a builder, real hard driving guy. He got things done. He was aggressive. The guy that reported to him for these years then was Lieutenant Colonel Nichols, Kenneth Nichols. And he reported to Groves, and he was an engineer also. And his quote was, "Groves was the biggest son of a bitch I've ever met in my life, but also one of the most capable individuals. He had an ego second to none. He had tireless energy. He was a big man, a heavy man, but he never seemed to tire. He had absolute confidence in his decisions, and he was absolutely ruthless in how he approached a problem to get it done. But that was the beauty of working for him, that you never had to worry about the decision being made or what it meant. In fact, I've often thought that if I were to have to do my part all over again, I would select Groves as my boss. I hated his guts, and so did everybody else, but we had our form of understanding."
Colonel Nichols actually ran the Manhattan Project from Oak Ridge.
Did
He did all of it with the scientific part in Los Alamos. He had the Hanford, he had the whole thing, and ran it right from Oak Ridge.
And he reported to Groves.
He did.
And Groves would come occasionally to Oak Ridge. Right?
Okay.
Nichols probably didn't want him to come too often. So Groves, take charge guy, immediately realized, asked the question, do we have enough uranium to mount the project? Well, I think probably Nichols heard about this, somebody heard about this, that there happened to be 1,200 tons of high quality uranium ore sitting on Staten Island in containers. And that this came from the Belgian Congo. A company in Belgian Congo had heard about the German interest in uranium. Joliot was the French nuclear physicist married to the daughter of Madame Curie. And so this company in Belgian Congo heard already in 1939 that the Germans were on to something involving uranium. And so they then shipped 1,200 tons of pitchblende, which is 65% uranium oxide. That's where you get uranium from pitchblende, to Staten Island. And it was sitting there. And this company tried to alert the US government for 6 months that they had this, but nobody cared or responded. Groves heard about this, I think sent Nichols up there, buy that uranium, buy that pitchblende. So all of a sudden, that problem was solved. Next problem was land. There had been a request lying on the table for months to buy 52,000 acres along the Clinch River in East Tennessee to have a reactor there, but nobody acted on that. Indeed, in the first meeting Groves had with his new superiors from the S1 committee, they wanted to get to know him, give him his marching orders, the middle of that meeting, he said, I got to go because my train is leaving to go to Oak Ridge to look over this, to go to East Tennessee to look over these 52,000 acres that he just authorized to buy, basically on his first day on the job. So Groves moved fast. Fermi and Szilard moved from Columbia to Chicago to try and build a better pile. You know, they had done this in Columbia, constructed a pile of uranium oxide and graphite, did not get high enough reproduction factor. Now they're going to try and do it better, get a K greater than 1 that would be on the way to a chain reaction. And so they came to Chicago to do this. Fermi calculated if you got it in the form of a sphere, well enough constructed, that you should be able to get a multiplication factor, reproduction factor greater than 1. So that was the next step, to build a better pile with better graphite and enough uranium oxide in the right kind of matrix. So all that stuff was shipped to Chicago. They started machining it, hard work, machining graphite bricks, machining bricks of pure graphite or graphite with little holes in which you embed the uranium oxide. The idea was the site for this next pile of tons of material would be out in the Argonne Forest. Compton and his wife and Fermi and his wife would sometimes go on a horseback ride out in the Argonne Forest, which is where Argonne National Lab is now, and they realized this would be a great site for building this reactor or this pile. Problem was that Stone & Webster was the higher construction company. There was a strike by their workers. They were supposed to start building that set of buildings in the Argonne Forest to allow Fermi a place to build his newest pile to show that you could make a chain reaction. So that delayed the site preparation. Time was of the essence. Fermi said, can't wait. And so his proposal was to go under the stands of Stagg Field. University of Chicago was a founding member of the Big Ten Athletic Conference in 1896. Their teams are called the Maroons. That's a trivia question you should always have when you go to a bar. And so that was Stagg Field. Amos Alonzo Stagg was one of the first great football coaches in America. And so this field was named after him. But Hutchins was the president of the University of Chicago. They decided to drop football in 1939. So by now, this time, 1942, the stadium wasn't being used. So Fermi saw this opportunity. They knew about a double squash court under the football stands. So, you know, under here, there was only one set of stands on the west side of the field, and under here in this corner, there was squash courts. And so Fermi knew about that and said, we could perhaps use the squash court for trying to build our pile, see if we could make it go critical. So he went to Compton, his boss, head of the metallurgical lab, said, let's do this. Compton conveniently forgot to tell the president of the university that they were doing this. Hutchins, the president, was a lawyer. He may have objected to try and build a device, a pile to make a chain reaction so close to downtown Chicago. So Compton didn't bother to tell him what was going on, but Compton got that space under the football stand for Fermi to try to build his pile. CP1, Chicago Pile number 1. So that's what Fermi and his team did. Construction of that pile began in November of 42. A tremendous, really a big construction project. There's no photographs, but this is kind of a drawing. You know, they have different layers of graphite blocks kind of in a spherical array, graphite blocks, and then 3 layers of graphite with uranium drilled into the graphite blocks. And they would build that up level by level. This is like 25 feet high and 22 feet high, maybe up to 57 layers or maybe more, starting from the ground up. And so that was heavy construction work, machining the graphite and the uranium oxide into these shapes. Then they had to also, they had to have a wood frame to support all of this so that you could put more and more on top of each other. They built control rods. Cadmium, they knew, absorbs neutrons like crazy. So they put 13-foot long wooden rods coated with cadmium sheets that you could stick inside of this ball that would then suck up the neutrons and stop a chain reaction. They started doing measurements of the radioactivity, of how much neutrons are there. They used indium foils embedded throughout. Neutrons hitting indium makes radioactivity that makes a Geiger counter click. So that's how they knew how many neutrons they were getting. And so that was the idea, to build up this pile. There is a small possibility that they knew that uranium-238, which does not fission easily, but it does have a small branch, a small possibility of doing spontaneous fission. And so that's how you get the neutrons, the chain reaction started. There is a small amount of uranium, spontaneous fission in uranium-238 that starts to produce the neutrons. And Fermi then was trying to measure at each level how close you're getting to a chain reaction, to a critical mass. So he would plot the square of the radius of the ball. Square the radius of that spherical ball of uranium and graphite divided by the activity. Radioactivity comes from neutrons hitting the indium foils. And as he added more layers, that ratio decreased. The radius was going up, but the activity from increased number of neutrons was going up faster. And so this ratio decreasing was an indication that you're getting more and more neutrons as you stacked up more uranium and graphite. And he could then extrapolate, say that when we got to layer 57, that we ought to have 0 ratio, which meant basically an infinite amount of activity, a very large amount of activity, meaning a chain reaction. So that's what they were doing. They were building up these layers, step after step. They were working 2 shifts, day shift, night shift, hard work. They then had 700,000 pounds of graphite, 80,000 pounds of uranium oxide, 12,000 pounds of uranium metal. This cost $1 million. That's a lot of money in those days to build this. There's no shielding, no cooling. If this worked, it could melt down and kill everybody in the room. But as they built up this number of layers, they had the cadmium rods in to absorb neutrons. And so then on the night shift of December 1st, they knew that they were close. They knew that by Fermi's plot, this trend was holding, and they knew that the next layer should make it go critical. So they stopped then, in the middle of the night. Fermi made them promise that they would not pull out the last control rod in the middle of the night. They put all the chemi rods in. They went home to sleep, came back the next morning on December 7th. By the way, that was A lot of things going on in the world. That was the second day where there was gasoline rationing in Chicago. The State Department that morning announced that 2 million Jews had died in concentration camps, and there were 5 more Jews ready for execution in concentration camps. They knew news that Germans were preparing a counterattack in North Africa. The Japanese-American battle at Guadalcanal was going on, a brutal battle. All that was happening the morning of December 2nd when they went to the football stands. Throughout the morning then, they were then taking cadmium rods out slowly. Fermi was measuring the radioactivity with a click of the Geiger counters, calculating on a slide rule whether this was on track. They stopped for lunch. They all left for lunch. They put in their control rods to shut it down. Came back after lunch. There were 42 people that assembled on the platform in this double squash court. He knew that they were doubling that when the last rod was pulled out, that he calculated by the radioactivity, the click and Geiger counters, that he achieved a K greater than 1. So they were multiplying neutrons now in a chain reaction. The number of neutrons was doubling every 2 minutes. They had achieved this. They had chain reaction. There was no shielding, no cooling. The calculation is that if he had let that cook for an hour and a half, they had been up to 1 million kilowatts, which would have melted and killed everybody in the room. So they knew the danger of this. People in the room were nervous. The Geiger counters were clicking like crazy, increasing every 2 minutes, doubling their intensity. When would Fermi shut this down? Well, he was trying to measure what was happening. And so finally, after 4.5 minutes, he said, put in the cadmium control rods, and they shut it down. And so they had achieved a chain reaction in those 4.5 minutes. Yeah, John?
So if
well, it would have melted down. Yeah, it would have melted. So that structure, you let it go for an hour or so, that whole mechanical structure would have melted down. That's what happened with reactors in Fukushima.
yeah,
They lost cooling. It was well constructed, melted. So that's what happened here. Then the chain reaction would have stopped because the cadmium would make it not be there. And the structure would have been melted, and then the chain reaction would stop. But in the process, there would have been a lot of radiation. It was 40 people probably cooked. So Fermi understood all that, and so that's why he shut it down after 2.5 minutes. And so they accomplished this. That was a huge step. And this is, they had a chart reader, but this is the case here where radioactivity was going up, Geiger counters going crazy. And there was no photographs, but this is a drawing of the 42 people, all in coats and ties, but next to the pile. Here's a guy taking out the last cadmium control rod, and that's in a photograph of Fermi. Fiona Woods was a graduate student of one of those people. That's the group of physicists that were there making this happen on this historic day, December 2nd, 1942, just about a year after Pearl Harbor. And so that's the end of the story. Then, of course, this then led to Oak Ridge and the graphite reactor.
So add one little story to this particular group of people. One of the individuals who was actually there, but did not get to be among the 42 that were there, was Alvin Weinberg. He was at the experiment, involved in it, but they assigned numbers. I don't know if they drew numbers or what, but they used a scheme to determine who could be in the room. And they set a limit, and he was, I believe, 2 past the limit.
So he
of
was in
people who
Chicago.
got to go. He was there and participated in the experiment, but he was not high enough in the echelon to get the right number. And I don't think they drew numbers. I don't believe it was that. I think they assigned numbers based on who was involved and what they were doing. So he was there as a helper. He didn't get to go and actually be in the room.
Albert Weinberg was director of Oak Ridge National Lab for 25 years.
Yeah, longest director we've ever had.
Right. All right, gang.